Okay, thank you. Yeah, so sorry I will speak in English because I guess, well, given the audience, I think it's probably better this way. Okay.
Which audience?
Well, as a whole. Maybe, okay, sorry. All right, so the plan is today I will talk about Chabauty's method in the classical case and maybe hint about about Mignon-Kim's nonabelian generalization, if I have time. And then in the rest of the lectures, I will talk about the recent paper by Lawrence and Venkatesh, giving a new proof, a new p-adic proof of Faltings' theorem, of the Mordell conjecture. All right, so here's the setup. So K will be a number field, S a finite set of places, including the Archimedean ones, and O is the ring of S integers. And then, well, so Faltings' theorem, it's originally the Mordell conjecture. So just to remind you, so if X is a nice curve, and nice means, okay, so over K, so genus G over K. Okay, so nice just means, is just an abbreviation for smooth, projective, and geometrically integral. And then if the genus is greater than 1, then the set of rational points is finite. And this has many proofs now. So, well, maybe a few. So if the first proof, well, there's a reason it's called Faltings' theorem. So Faltings in 1983. And his proof he used, well, at some point he used some delicate calculations of heights, some Arkelov methods. And then Voita gave a proof that was simplified by Bombieri. Yeah, maybe you're wondering how Bombieri managed to simplify it before. I mean, he's a smart guy, but no, these are the publication dates. So, okay, all right. Anyway, so yeah, and this was using Diophantine approximation. And now recently, so there's this new proof that I will. The new proof of Brian Lawrence and Akshay Venkatesh. So the preprint, the latest version of the preprint is dated 2018. And this uses p-adic period maps. So I'll say what this is later on. All right, and there's an analog of this for integral points. So maybe so the Ziegel's theorem. So actually, let me state a version that also includes this one. So it generalizes Faltings' theorem. So okay, so for this, instead of a projective curve, we have a curve that's possibly it's still smooth, but possibly no longer projective. It could be an affine curve. So it'll be so any such curve will be the complement of a finite set of points inside a nice curve. So this is nice, so genus G. And Z is supposed to be some zero-dimensional subscheme. So geometrically, it's some finite number of points. And then you can define the Euler characteristic to be the Euler characteristic of X, which is 2 minus 2G, minus the number of points that were the number of punctures, the number of points removed. Okay, so, and in order to talk about integral points, I need to talk about not just U over K, but I need to have an integral model. So let me choose an integral model. So curly U will be, and it doesn't really matter so much what model I take for this statement. So any finite type O scheme So O is that ring of S integers, yeah, such that it's when you base change it to the number field, it's you recover the curve over K. So then the statement is that if the Euler characteristic is negative, so I mean, this is the analog of saying that G is greater than 1, because that's what happens if there are no punctures. Then this is just saying G. Then the set of O points is finite. All right. So okay. So maybe I'll say okay. So I mean, this one implies this one. Because you can specialize to the case where there are no punctures. On the other hand, Faltings' theorem also implies, I mean, in a slightly less direct way, and that's just because if you know Faltings' theorem and you want to prove this statement, you can replace U by a Galois étal cover, if necessary, to increase the genus. So it has a Galois étal cover. So yeah, so you can use this argument of passing to a finite Galois cover that goes back to Chevalier and Vous. So genus greater than 1. Okay. So all right. So okay. So let me say something about the proofs of this statement. So again, here there are also several proofs. So first, oh well. Okay. So let me say okay. I mean, let me talk about the affine case. So where there are some punctures. So it's easier in this case. So and in this case, the first proof was due to Siegel, 1929, and this was using Diophantine approximation. And it was this proof that, in some sense, Voita generalized. And then in around the late 60s or early 70s, Allen, Baker, and Coates gave a proof based on linear forms and logarithms. And now there's also there's another proof. Well, I guess in some sense it just follows from this, but it's in some sense this argument of Lawrence and Venkatesh, you can adapt it to integral points as well at least in certain cases. So this so again p-adic period maps. Okay, but none of these are what I'm going to talk about today is something that predates all these proofs, and also here. So here there's.
That's a quick question.
Yeah.
For Baker Coates, is that in total generality or is it just for hyperelliptic curves?
So I believe it's. Let's see. Let me think a second. Oh, you might be right. Let me think. Sorry. For hyperelliptic.
Like I thought it was something like an effective bound on integral points on the height of an integral point on a general curve is not known except for like
yeah. So I think you might. Yeah, the effective. You're right. The effective is. Yeah. Sorry. So I guess you're right. Sorry. So this is. I should say this is only for hyperelliptic. So. Yeah, or something like that. Yeah, hyperelliptic.
Yeah.
Sorry. You can.
What you can do with linear forms and logs is the unit equation.
Yeah, that's what. Yeah, the linear forms and log give the S unit equation, right? And then from that, anything that you can get by taking finite étal covers of that will be this. Yeah, so you're right. So this is only for those. But I guess the nice thing about this is that this one's effective, whereas this is not, and this one probably isn't either. At least it's not clear. Okay, so yeah, so okay, and here there's also. So okay, so what I want to talk about here is an earlier argument that's due to Chabauty. So 1941, but this is again also is a partial result. that says that if the rank of j of k is less than j is going to be the Jacobian is strictly less than the genus, then the set is finite. And actually, Chabauty was inspired by an analogous method here that was of Skolem that also had only a partial result. So. Okay, so this is what I want to. So it's Chabauty's method that I want to explain. So let me. All right, so here's the setup. So x, okay, so x is as in Faltings' theorem, nice curve of genus. Well, I mean, I'll again assume it's genus at least one. And actually, just for this exposition, although I don't really need it, I'll assume that it's that the number field is Q. Yeah, so let me just say, yeah, so K is equal to Q. This is for simplicity. Yeah, so this is over Q. And P will be a prime. I mean, it's a p-adic method, so I need to choose a prime. So it's P. And you can make it work when x has bad reduction at the prime, but it's easier to describe when it has good reduction. So, and I can choose, so let me do that. And J will be the Jacobian of x. So that's an abelian variety of dimension G over Q. And also, I'll assume that we have a rational point. I mean, well, if there's no rational point, then the theorem's true. So it's OK. Yeah, there are also ways you can get around that. If you're trying to do something effective and you don't necessarily know if there's a rational point. But OK. All right, so anyway, once you have the rational point, you get an Abel Jacobi map. You can embed x in the Jacobian by mapping P to this, to the class of this divisor. All right, and the method's going to use the group of QP points on J. So I want to understand that. And one way to understand is using the logarithm, the p-adic logarithm. So which can be described in terms of integration of one forms. So let me take a global one form on the Jacobian. So yeah, so this thing is some g-dimensional. This is some g-dimensional vector space over QP. So given a one form, there exists a unique homomorphism. This is going to be a p-adic integral. So from the p-adic points to QP, and that. So okay, I'll denote it this way. It'll be the integral from 0 to p of omega. Now, okay, so what does that mean? Well, it's characterized by what it is in a neighborhood of the identity. And I mean, it suffices to describe it in a neighborhood of the identity because this is a compact group. So any neighborhood of the identity will contain a finite index subgroup. And then this is taking values in a torsion-free group. So it suffices to give it. So the neighborhood I'll take will be the residue disk of 0. So all the points that reduce to 0. And in that neighborhood, it's given explicitly by expressing omega, expanding it in power series in local parameters. So choose local parameters t1 through tg at the origin, and then omega is some multivariable power series times dt1 plus another power series times dt2, et cetera. And okay, and once you have that, then and you can integrate. You can integrate formally to get just to get, and then, yeah. And the result is that that's okay. So it takes some work to prove that's well defined, but anyway, so that's it. And so if you vary omega, then you can view it as a pairing. And or equivalently, you can view it as a, yeah, and this is QP linear in the second argument. And so you can also view this as saying that each point here gives you a linear functional here. So you can view it as a map to the dual vector space. And this is the space of global one forms on J, which is isomorphic to the cotangent space of the origin. Because if you have a cotangent vector at the origin, you can translate it around by the group law to get a global section of the cotangent bundle. So yeah, so this is just the dual of the cotangent space of the origin, which is the tangent space of the origin, which is the Lie algebra of that. So I'm just thinking of this as a vector space. So it's the tangent space of the origin.
But maybe you can also give an elementary p-adic interpretation. You just for each given form omega, you have an analytic p-adic analytic homomorphism from the group of p-adic points of Jacobian to QP. Therefore, there is a tangent map, and this tangent map is exactly a form omega.
Sorry, you're saying there's a map from
Yes.
the.
Yes.
Oh, you want to use the formal group instead? No. What are you saying?
It's much more elementary.
What is more elementary? What are you proving?
I am proving that. I am proving that I am given an interpretation of this homomorphism.
Oh, this one.
Yes.
Okay.
Yes. You have homomorphism from G of QP
Mm-hmm.
to QP,
Yes.
which is actually a group homomorphism.
Yes. Right.
It's analytic homomorphism.
Yes.
Therefore, there is a tangent map. And this tangent map is exactly a form.
Oh, but how did you get the homomorphism from J of QP? That's to this. I mean, that's what I was trying to explain.
Well, you just take p-adic logarithm and the neighborhood.
Okay, that's what this is. Yeah. Yeah. Okay. How do you get the p-adic logarithm? You integrate invariant one forms. Okay. Yeah. Okay. Anyway, yeah. I mean, I guess there's a Bourbaki way of doing it too, where you don't even talk about one forms. Maybe this is what you're thinking of, where you essentially take you take a point and you take multiples of it, and if you take a multiple that's more and more divisible by higher and higher powers of p, then those multiples will converge to the origin, and then you can scale. Yes. So you can define it that way as well. Okay. Okay. So, all right. So this is a homomorphism because of each of these individual. And also, I mean, you can say that not only is it a homomorphism, but I mean, it's also a local diffeomorphism. Because you can compute the derivative of this map, and it's almost by definition. I mean, the tangent space of the origin here is the same as the tangent space of the origin here, and then the derivative is just the identity map on the origin. So it's a local diffeomorphism, and also GFQP is compact because it's the same as the ZP points, and so if you put these two together and you use just basic things about topological groups, you find that the kernel has to be the torsion subgroup, and the image has to be some compact subgroup here. So it'll be, but I mean this thing here is just isomorphic non-canonically. I mean, if you choose a basis of the one forms, it's a g-dimensional vector space, and so a compact subgroup here is going to be is going to be is going to be a free module of rank G. So yeah, so this is okay. So this tells you a lot about this group. Yeah, and also this thing is this kernel is finite because it's a discrete subset of a compact group. And so yeah, so the whole group is just an extension of ZP to the G by a finite group, and it's commutative. So actually, what this tells you is that J of QP is actually just a direct product of ZP to the G and some finite abelian group. And so, well, anyway, I don't really need that, but maybe I'll just say, I mean, it's approximately equal to ZP to the G. So this kind times a finite group. And maybe I can say more precisely, it contains such a group. So maybe I'll introduce a new symbol here, which is like approximately, what? Oh yeah, sorry, P. Okay, so this new symbol means it's approximately, I mean, it contains this, and also it has finite index. So, all right, maybe this is a bad idea, but okay, so contains as a finite index subgroup. Okay, so essentially it looks like ZP to the G. That's what J of QP looks like. On the other hand, we know that we have the Mordell-Weil theorem, which tells you what this looks like. I mean, this is a finitely generated abelian group, so I guess it approximately looks like Z to the R up to some finite amount. Yeah. Okay, so let me now. What happened? You don't like my notation?
No, I'm laughing about the fan.
Oh, man. Do you want me to turn it on, by the way?
Well, yeah,
What?
if you don't want it that close to you.
As long as it's facing that way. Do you want it on?
Yeah.
Yes?
Yes.
Okay, I mean, it's going to make noise, you know. All right. Oh, I could. Yes, is it okay? All right. So, okay, so let me just start by giving an example. And for this example, I'll suppose that the genus is 2 and this rank, the Mordell-Weil rank is 1. Okay, so then, then J of QP looks like ZP squared, and then the Mordell-Weil group is rank 1, so it's essentially the multiples of one rational point, and yeah, so if I were to draw a picture of it, so here's what J of QP would look like, and yeah, and then inside there you have the curve, so you have x of QP. On the other hand, you have the Mordell-Weil group, which is, so let's say this is O, and then you have the multiples of that point, etc. But I mean, these are multiples inside what's essentially a ZP module, and therefore the multiples don't get bigger. They just are all contained inside a ZP submodule. And so if you take the closure of this, yeah, so then you can, the closure of the rational points, so this means, this notation means the closure of J of Q inside the p-adic points. So then this is going to look like, I mean, up to this finite index, it's going to be the ZP multiples of this, which makes sense inside this ZP module. So the multiples are not dense the way they would be if you try to do this argument over the real numbers typically. So they will span something. In this example, they will just span a one-dimensional analytic submanifold of J of QP. And so now, if you take the if you take the intersection of these two analytic submanifolds, so then this, well, first of all, I mean, the reason we're interested in this is that this contains, I mean, rational points must both lie on the curve, must both lie in the QP points, but they also must map to rational points in the Jacobian. So they lie in here. And then this, well, it's going to turn out that this is zero-dimensional. I mean, just as you would expect from the dimension counting. I mean, if they're two one-dimensional things and a two-dimensional thing. And on the other hand, it's compact because these are all closed subsets of a compact group. And so hence it's finite. So yeah, so this gives you a finite upper bound on the set of rational points. So this proves the finiteness under these hypotheses where you have this rank and genus. And what holds in general, okay, so that was just the example, but in general, if you look at this closure, then this is going to look like essentially it's up to finite index. It will look like some ZP module, but it'll look like a ZP module spanned by R points, up to finite index. But that span could have smaller rank than the rank of the group of rational points, and that's just because, well, so y less than or equal to, I mean, that's just because, I mean, the points in the Jacobian are z independent, but z independent points inside zp to the g, which inside the qp, they are not necessarily ZP independent. So there could be, I mean, a priori there could be some ZP relations. In fact, there have to be if the rank is greater than the genus. So, all right. So, yeah. So now I can state Chabauty's what Chabauty actually proved. Okay, so Chabauty's theorem. So at least one form of it is that if this R prime is less than G, which is automatic, if the rank is less than G, because R prime is even less, then this intersection inside J of QP is finite. And so okay, so as a corollary, then the set of rational points, which is in there, is also finite. All right, so let me sketch a proof of this. So we have to show that So, I mean, in fact, I'll sketch a proof in a way that'll give more information. Actually, let us compute some specific examples. So the first thing I want to do is look at these one forms on J. You can pull them back, the global one forms. You can pull them back by the Abel-Jacobi map to get global one forms on X, and it's just a well-known theorem of geometry that this is an isomorphism of, and so this is some g-dimensional vector space. So let's choose a basis. So these are one forms on X, and now you can understand everything in terms of this diagram, where you have J of QP. You have these two two submanifolds mapping into here. And then we know that the rational points in the curve are contained in both of these. So, okay, so we want to understand the intersection of these images here. But I mean, the way we understand this group is via the logarithm, the p-adic logarithm map, which, as we said, goes to this QP vector space, which is. And so instead of considering the intersection here, we'll just map everything into here and consider the intersection here. I mean, this is just a map with finite kernel. So I mean, essentially very little information is lost in passing from here to here. So it suffices to prove the finiteness of the intersections here. And yeah, so and now this map, this is the Abel-Jacobi map, and then composed of the log, and this map was obtained by integrating one forms on J. And now, so if you look at this map here, this is going to be sending each point to, well, you can pull back the integrals and get integrals on x. And so this will be the integrals from, these will be some p-adic integrals along x. I mean, if you want, this is just notation. I mean, one way to define these integrals is to pull back. I mean, is to define them as these composition. But I mean, it's also true that these things can be computed if you have 2 points that are close together. Then you can again compute this formally. And now you just have to expand these in power series in one variable. And so now you're just integrating power series in one variable to compute these things. At least if you're integrating between 2 points in the same residue disk. All right, so you have this picture. All right. Okay, so now I want to use the hypothesis that R prime is less than G. I mean, the reason that's relevant is that, I mean, G is the dimension here. It's a dimension. And R prime is the dimension of this. So if R prime is less than G, okay, so if R prime is less than G, then this closure is contained in the zeros of this integral. So okay, it's a function of this upper point. So this is for some non-zero omega in h0 of j. Yeah, I'm just using the fact that, I mean, if you have a ZP submodule in here of rank less than G, I mean, it's contained in some hyperplane. So there's some linear functional here that vanish on it. So as a function here, it's going to be, yeah. So inside here, it'll be given by the zeros above one of these linear combinations of these integrals. And so, okay, so that means now if you pull everything back to the curve, then this will then be contained in the zeros of the pulled back function if you restrict these integrals to the curve. And now you'll just get integrals of the corresponding one form on the curve over QP, which is going to be some non-zero one form on the curve. So yeah, but this integral, so this integral is, as a function of this upper point, is on the curve, is given by, well, it's given by a non-zero power series on each residue disk. in the p-adic points on the curve. So yeah, and that, I mean it's non-zero because, well, since it's non-zero, since it's you can, if you take its derivative, you take the differential, it's omega, which is not zero. And so, okay, so now you have a power series. I mean, on some residue disk, which is some I mean, if you're just looking at the QP points, it's just some compact closed disk, and then you have a power series that converges in a radius that's on open disk that contains the residue disk of p-adic points, and so it has finally many zeros. And then you have that for each disk, and so you finally manage residue disks all together. So that finishes the proof. Okay, so all right. Any questions about this argument?
I just want to know where in your argument are you using the times good resolution?
Oh yeah. So I mean, I didn't really use it very seriously. I mean, I did it just in order to, I guess, in order to, I mean, it essentially all works even if it's a bad reduction. The only thing you have to change, you have to think about what it means to talk about the residue disks. And then, so for that, you probably want to work with the narrow model of J and then the minimal proper regular model of X. And all the points will be in the smooth locus of that minimal proper regular model. And then you can do essentially the same argument. So, yeah, any other questions? Okay, so let me now try to make this a quantitative. So here's a quantitative version of this. So now I'm following arguments of Robert Coleman. So okay, so we want to know how many, I want to say how many zeros can such an integral have. And so before doing that, let me scale, I mean, I'm free to scale omega by any non-zero number in QP. So let's scale it so that it reduces nicely, so that it reduces to a non-zero form on the mod p. So x over fp. Okay, so I mean it's in, yeah, okay, so and let me focus on one residue disk. So the residue disk are the things that reduce to a particular fp point. So I'm fixing one fp point, and I'm going to talk about all the qp points that reduce to it. And let me let m be the order of vanishing of this differential at this fp point. Okay, so this is some non-negative integer. And then the claim is that if the order of vanishing is less than p minus 2, then the number of points in X, the number of rational points that reduce to Q tilde is going to be bounded by m plus 1. Okay, so I mean, by the argument we gave, I mean, this number of points, all these rational points are going to be zeros of some analytic function. And so this really is a lemma about counting zeros of some power series. And so to prove this, well, we'll just write everything out in terms of power series. So, I mean, the omega that we're integrating is, I mean, what does it look like in terms of the local coordinate? I mean, it's some power series in the local parameter t. So okay, so I've chosen a local parameter t at this point q tilde, and then p-adically it looks like this times dt with And I've scaled it so that this thing reduces mod p, so omega is actually in h0 of x sub zp over omega. And so that implies that if you choose the parameter well, then this expansion will have zp coefficients. And also we know something about these coefficients. We know something about the coefficient of the mth one, because I told you that m was the order of vanishing mod p. And that means that the first coefficient here that's a unit is going to be the mth one. So this, and so in particular we know this, this valuation is 0. So that's, okay, so that's the one form, and now we have to integrate it. But integrating is easy. We just integrate it as a power series, and it's just going to be now, it won't have ZP coefficients anymore because there could be some, I mean, you know how integration works. You sometimes get denominators. So yeah, so so this integral, sorry, the integral will be, well, in terms of t, it will be some, well, okay, it'll be like I think that's right, something like that. Maybe there's a constant of integration. I don't know, plus constant. Okay, whatever. So, so it's some power series like this, and we want to count the number of zeros of this. And so, in order to do this, we can look at the Newton Polygon. So where you of this integral. And so, what does that look like? I mean, this is where you at each. For each I, you plot the valuation of the coefficient of t, the I. And so, well, okay, so the first few coefficients here are all the coefficients are in ZP. And so the first time that you could possibly get a denominator that's, I mean, something that has negative valuation would be where? That would be, well, when you get to t to the p over p. And so, okay, so at p there could be, I mean, I don't know where it is, but I mean, it could be anywhere up here. And then once you get way out,
Can I ask a dumb question? Did we say that this point that we chose 0 reduces to p tilde or p or something?
yeah. So sorry, the point, yeah, t is a local parameter. On x sub zp, such that t at q tilde is 0. Yeah, I should have written that. Is that your?
I think I'm just confused about the integration is happening only in a residue disk or something?
Yeah, this integral. So these things, this makes sense. Yeah, for absolute value of t less than 1. p-adic absolute value less than 1. Is that, yeah? But actually we're interested only, because we're actually interested only in zeros. So what we want are zeros that correspond with t that lie in p-zp. Because those are the ones that reduce to 0.
Yeah, I was just asking about the notation integral from 0 to omega.
Oh yeah, so this is a function. It's a function of a point, but I've parameterized the residue disk by t. So I'm thinking of this now as a function of t, in the same way that my omega was viewed in terms. I've expressed in terms of t. Yeah. So I'm really okay. So now I'm thinking of this as this is some convergent power series. It converges on disk of radius 1. But all I really want are the zeros inside this smaller disk of this inside here. Yeah. So so we want this set of zeros. Yeah. So okay. So what does the Newton polygon look like? So we said there could be a negative valuation and the coefficient of t to the p. Now there's one other thing we do know: if this coefficient is a unit. And so when you integrate, a sub m is going to be the coefficient of, well, divided by something, will be the coefficient of t, the m plus 1. So somewhere here at m plus 1, there will be a unit coefficient. And the assumption on m, where was it? M is small enough so that m, it really is to the left here. M plus 1. In fact, not only is it to the left, m plus 1 is at least, m plus 1 can't be any more than p minus 2. So there's actually at least another 1 point in between here. So it really looks like this. And then everything before there, these are also all units. And so these are all, I don't know where they are, but yeah, this one is really there because it is a unit. The other ones could have even higher evaluation. And then there's something here. And then, well, if I go way out to p squared, then I guess I could get a p squared. I guess in between there could be like a 2p. There could be some negative things. Okay, etc. Okay, and eventually you could get really negative coefficients, but it takes a while. And now what we're interested in are the zeros of valuation greater than or equal to 1. And so these correspond to slopes of segments of slope less than or equal to minus 1. So valuation greater than 1 corresponds to slopes less than or equal to minus 1. So we're looking at negative slopes. And you can see that however this Newton polygon goes, there are not going to be any, slopes beyond this point that have negative 1. All right, so I don't know what this looks like, but because even this first slope here, which is the most negative of them all, it can't be any worse than minus a half because this is a width of 2. And so that means that all these slopes here are the only part here. These are all the slopes with this width. They're all going to be in this part. And so here the width is m plus 1. And so and the width of the segments tells you how many zeros there are of each of that valuation. And so the total number of zeros is at most m plus 1, which is what the theorem said. Okay? Any questions about this? Yeah, Coleman did, you can do this analysis even when this hypothesis doesn't hold, even when m is larger, but then, the answer will be different. It's more complicated because you have to worry about the fact that this might have gone down a little bit. But you can still, it's a little bit, yeah, it's a little bit annoying, but you can do the calculation to figure out what's happening. Sorry, what do you say?
The first point when you do
that was the coefficient of t to the p. That's t to the p. No, because this is how integration works. So when you integrate t to the p minus 1, you get t to the p over p. And so the term that could have a p in the denominator is the coefficient of t to the p. So okay. All right. It comes from the previous coefficient of t to the p minus 1, but that's not what I'm plotting here. Yeah. All right. Okay, so all right, so okay, and using the, if you do this argument for each residue disk and you add up the results, you can get an explicit upper bound on the number of rational points. That just depends on, and well, if p is large enough, then you're guaranteed. The total number of zeros of omega tilde is at most 2g minus 2. So if p is sufficiently large, then you know that this will always happen, and then you can use this for all the residue disks, and you add them up. And you'll get some bound for the total number of rational points just in terms of 2g minus 2 and the number of residue disks. So this is what Coleman did. So okay, I'm not going to write that out. But by the way, this is all written up in a survey paper that I wrote with Bill McCallum. And so I'll give the references. Maybe it's already on the website. I emailed them to Emmanuel yesterday, but. And I'll also give references for the future lecturers too. All right, but now let me just do one example just so you can see how this works in practice. So let's take this polynomial. You might wonder where this polynomial came from and whether I've chosen it especially so that things will be nice. But no, it came sort of naturally in a paper that I wrote with Victor Flynn and Ed Schaefer a long time ago. And we actually used Chabauty's method to find the rational points here. And after, well, I mean, many years later, we found that it's actually much easier to do Chabauty than we thought we would. So I'm going to show you the easy way. All right. So I mean, it's going to be so easy that I can do it without a computer. Well, except for the part about doing a 2 descent and computing the Mordell-Weil rank. But all right. OK, so my curve is going to be the smooth projective model of, it's going to be a hyperelliptic curve of,
Can I ask a maybe another question?
yeah?
So suppose I have this Chabauty hypothesis. Of course, you produce some like explicit in the sense that you can compute up to arbitrary p-adic precision each of the elements. You produce some explicit finite set inside which the rational points lie. But am I supposed to think of like it's another computation person? If I have the Chabauty hypothesis, there's a very good chance that some prime will actually cut down this set to just the rational points or something, or
OK, so that's a good question. So the question is, if this hypothesis about rank less than genus holds, do you expect that if you choose the prime carefully, that you can actually get a bound?
like on computation grounds, not
Yeah. So, but I think the answer is in general no, and the reason is, well, what typically happens is that most residue disks, well, it often happens that each residue disk will contain 1 0 of the function just because of the way these integrals work out. You have a, and so you expect to have the number of the bound you get is usually it usually involves the size of the number of points in the residue field. And so if your residue field is too big, then, I mean, for large primes, it's not going to work anymore. So really, if usually what happens is if you're going to make Chabauty work, you're going to make it work by choosing a really small prime. And if those first few primes fail, then you're kind of out of luck as far as applying Chabauty directly. On the other hand, if there are ways you can enhance Chabauty by combining it with something called the Mordell-Weil sieve, where you not only look at this p-adic method, but you reduce modulo other primes, and you ask what's the condition for the point, for a point to lie on the reduction. Actually, wait, this came up in one of the talks last week. No, was it Felipe? No, Brendan. Yeah, Brendan discussed this method where you look at the curve of the points over some other finite field, and you map that into a Jacobian. And then you can get constraints on where rational points can live by saying that they must reduce to points in the Jacobian that are in the image of the FL points of the curve. And by doing that for several primes and using some kind of Chinese, well, it's not exactly Chinese remainder, you can get congruence conditions that can often rule out the unwanted points in here. So in practice, it seems that in practice, usually you can do it if the rank is less than the genus. So, okay, so all right, so let's do this example. So X is this genus 2 curve, and explicitly, if you want to say how to get this smooth projective model, I mean, you don't just take the closure in P2. That'll have a horrible singularity at infinity. But instead, you can consider it inside a weighted projective space. So if you take this polynomial and you homogenize it, so you let this be the associated homogeneous polynomial. So now it's x to the 5th z plus dot 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 plus z to the 6th. And yeah, so then x is isomorphic to, you can define it as the proj so you take the weighted projective space, and you inside the weighted projective space you take this you take the equation that says y squared equals this homogeneous version, and this is a weighted projective space where x and z have degree 1, but y has degree 3. That's just to make it so that this polynomial really is homogeneous, weighted homogeneous. So yeah, so okay, so this is the projective curve and contains this one as one of the affine patches, the patch where z is not 0. Yeah, but the point of doing this is you can now see all the rational points. You can see all the points, including the ones that are infinity in the original model. And so, okay, and this you can also see the double cover of P1 in this model, because it's just, I mean, P1 would just be the proj of just this polynomial ring with the usual grading. Okay, and now what the goal is to calculate the rational points, and I'm going to tell you what the answer are, what the answer is, what the set of rational points is. So it's well, okay, there's some obvious rational points. Anybody see one? Somebody said plus and minus infinity. Okay, yeah, 0. That's maybe obvious if you're used to that kind of thing. Yeah. So yeah. So I think the most obvious ones are the ones with x squared and 0. I mean, if you're really good at calculating quickly, you could see that minus 3 also works. Okay, so those turn out to be all the points on the affine curve. And then there are also 2 points at infinity. As you can see from this model, so the points at infinity are the ones where z is 0. But then because this is x to 6, you can take x equal 1. And so you get some points where you take z equals 0 and x equal 1, and then y can be plus or minus 1 again. So okay, I hope it's not disturbing that I've written my points in 2 different ways. I mean, these are projective points on this, and these, if you want to have these in all the same form, you'd put this colon, and then z equal 1 on each of these. Okay. All right. Yeah. So these points, I mean, some people call these points. There are 2 points that lie above 1:0, which is the point of infinity here, and so these are sometimes called infinity plus and infinity minus. All right. So yeah. So, and notice that each of these has a plus or minus. So this is actually 6 points. Yes? 6. Yeah. Okay, so we're hoping to do Chabauty and get an upper bound that says that the curve has at most 6 points. Because then, and that's the only way that Chabauty can really work and give you all the rational points. If the upper bound you get is actually the number of rational points that you know. So. All right, so let me prove this. Okay, so the first part is you somehow have to figure out the rank of the Mordell-Weil group. And the easiest way that I know to do this is to do a 2 descent. And yeah, in this case, it's actually not so bad because it turns out that this curve has only 1 prime of bad reduction. I mean, it's a big. I think if I remember right, it has bad reduction only at 3701, and so, but also at 3701, it has the simplest kind of bad reduction, which means because of for various reasons, it means that the Tamagawa number there is 1, and so you can essentially treat it as if we're a good prime, as far as computing the Selmer group is concerned. Anyway, so you can actually do this essentially without almost no calculation also. But I don't want to that's a different story. So let me not talk about that. All right, now I have to choose a prime for Chabauty, and I'm going to choose p equal 3. And so there's going to be some omega tilde that comes from the special omega that came out of this proof. The omega, there's some omega whose integral vanishes on the rational points, and this omega tilde is going to be the reduction of it, scaled appropriately. So okay. Yeah, and for a genus 2 curve, the one forms are, I mean, for an elliptic curve, you know that it's just spanned by dx over y. For a hyperelliptic curve of genus 2, you get that and also x dx over y. So this omega tilde we're looking for is going to be some combination of these. And also the omega itself is going to be some z3 combination of these. All right. And, oh, OK, we also know, well, it's easy to figure out what the f3 points are. I mean, this will tell you what the, it turns out that they're just the 2 points infinity and these 2 points. So this is all mod 3. I guess you can probably figure out why I didn't write this when I'm considering it mod 3. It's those are the same ones, yeah? So, OK. Now, OK, here's one thing I can say. If I look at a residue disk, in other words, a point mod 3, and it's such that the order is 0, notice that 0 is less than p minus 2. So if this happens, if I'm looking at such a residue disk, then I can apply this quantitative lemma. And that says that its residue disk has at most 0 plus 1 points. So it has at most 1 rational point. OK, so I have this. So, but what happens if I take the residue disk that reduces to 0, 1, say? I already know that it has at least 2 rational points in it. Namely, I have 0, 1 in there, and I also have minus 3, 1. So OK, so what can you conclude from that? Well, that this hypothesis must fail. So the order of this omega tilde, this unknown omega tilde, is at this point is going to be strictly greater than 0. And this is a typical way of how Chabauty works. It helps a lot if you already know some rational points, because having rational points and knowing that your integral of the omega has to vanish on those rational points, that gives you constraints on what omega can be. And so here, using the fact that we have these 2 rational points in the same residue disk, we can figure out at least we can figure out, yeah, we can figure out what omega looks like. In fact, we could do even better. We could figure out what omega looks like even p-adically using the integral between these 2 points. We could find which combination of the integrals of these between these 2 points gives 0. And so, OK, but anyway, this is all I need for now. So the omega tilde has to vanish at this point. And if you look at these combinations, I mean, one of these obviously, this one vanishes there because x is 0, and this one does not vanish if you work it out. Well, so this tells you that omega tilde is actually equal to the second one as a differential on the curve mod 3. So well, it's up to, I guess it could be a scalar multiple, but it doesn't really matter. I mean, you can always scale omega anyway, so up to a relevant scalar multiple. All right, so yeah, so to summarize what I know at this point, well, I mean, now that I know what omega tilde is, I can tell you what its order of vanishing is on each residue disk, at each point. So it's going to be 1 if q tilde is equal to one of these 2 points, and it's going to be 0 if it's one of the other 2. If it's, yeah, so, OK. Now, so in this first case, well, let's do the second case first. So here the order it satisfies this hypothesis. So I know that in these residue disks, so these have at most 1 point, 1 rational point per disk. So this is by the quantitative lemma. which is the right number. That's the right bound, because that's how many points there are in those two disks. There's one of these rational points in each of them. So that's good. So now, unfortunately, I can't use the quantitative lemma for these because the hypothesis, I mean, this hypothesis doesn't hold. The order of 1 is not less than p minus 2. So, but I can still try to use Newton polygons, etc., and see if I can. Well, I can look at the Newton polygon. I'll have to redo this argument to handle the fact that I have a potentially now that this point has dropped by 1. So I have to analyze that. Okay, so let's focus on one of these residue disks. So let's look at the residue disk of 0, 1. So I have to choose a uniformizing parameter. So let's choose the uniformizing parameter x. And so I want to expand on my differential. I need to express my differentials in terms of x. So in doing that, I can do it by expanding. Well, I have this plus blah, 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 5x squared plus 6x plus 1. I need to expand this as a in terms of x. And so I do this using the binomial theorem, this is 1 plus something raised to the 1/2. So you can expand it out. You'll get something plus 1 plus 3x plus blah, blah, blah. And actually, all I really care at this point is what it looks like mod 3. And mod 3, this looks like 1 plus 2x squared. And so when you take the square root, it looks like 1 plus x squared plus higher order terms as a power series over f3. And so omega tilde then looks like x dx, which is x dx over y. That's going to, if you substitute this in here and you do the power series division in the power series ring over f3, it's going to look like, yeah, and then multiply by x. It's going to look like this times dx as an element in f3. Okay, so if you want to know what omega it has z3 coefficients, but it reduces to this. So, well, it's going to look like this plus mod 3. Okay, so now I can look at let's now look at the Newton polygon. So, yes? The equation is behind the fan. All right. I don't know if, okay, sorry, this is probably. Well, it's probably better for you and worse for them, but they already saw it, probably, so. And, okay. Sorry, maybe that was that too much? Oh, it's great. Okay. All right. I mean, I haven't been getting any of this, so. Okay, so all right, so I know what omega is. At least I know approximately what omega is periodically. At least I know what it looks like mod 3. And so what do I know then about the Newton polygon of the integral of that power series? So okay, so I guess I'm integrating from the point 0, 1 now. Yeah, so. Well, let's see. So there's an x term. Okay, so there's a coefficient. There's a t squared over 2 that gives me a definite point there. That's from integrating the x. If I integrate the x cubed term, there'll be a definite point there. Actually, I probably don't even need that. But now then, I mean, the danger was that there could have been an x squared term that when I integrate it would have given me like an x cubed over 3. But I got lucky. So, because there was the coefficient of x squared was divisible by 3. So actually, instead of getting something down here, which I could have a priori got, for this particular curve, I know that it's not there. It's actually here or above. And so the first time when I could have a negative valuation is at the t the sixth coefficient, where I could have something down here. But that's OK, because already the Newton polygon then, at worst, it's going to be like this. Well, OK, I guess there could be something at t the ninth as well. Well, OK, anyway, the point is there's nothing, there are no points below or on this the line where that would contribute segments of slope -1. These are all lesser slopes. Even if I go out to 9, then they get a -2. So yeah, so the worst I guess could be something like this. But then so all the zeros are going to be all the segments of slope -1 are going to be in here. And therefore, the conclusion is that the number of rational points reducing in this residue disk is going to be is the width of this, which is 2, which is what I hope for, because that's how many rational points I already know. And so that gives you okay, so that means there are 2 zeros, and yeah, and then the same argument applies to the other. I mean the other one is essentially the same, because it's just equivalent to, you can just apply the hyperelliptic involution to see what happens in the other residue disk. So okay, so yeah, so the same. The same for the residue disk of 0, -1, and so the total. So the total is that the bound you get is for the number of rational points is at most 1 + 1 + 2 + 2, which is 6. So great. So we found them all. So that finishes the proof. All right. All right. So let's see. So. Yeah.
So you mentioned this was the easy way. Does the hard way require you to compute the whole nonabelian group and use that to find omega?
Yeah. So the way we originally did. Let's see. I'm trying to remember what we. I don't remember actually, but we did something. This is like 20 years ago, so I don't remember exactly what we did, but we had to work harder for some reason. I think also maybe we were using a different. So Victor Flint had a different method where instead of. Here we've sort of taken these functions on the Jacobian and restrict them to the curve. There's another way of doing it where you take the equations that define x of qp inside its Jacobian and you restrict them to the closure of the Mordell-Weil group, and you view it as a function of n, where you're looking at n time, whether it vanishes on n times p, and then you try to solve for the n's that. Yeah, I don't know if I'm making sense. There are 2 ways you can compute it. There are 2 ways you can compute an intersection of 2 curves. You can take the function that vanishes on this one and restrict it to the other curve, or you can take the function that vanishes on the second curve and restrict it to the first curve. So there are 2 ways of doing it, and anyway. But I think the way I did is much easier than the other way. Okay. All right, so let's see. So we got about 12 minutes left. All right, so that's all I'm going to say about the classical Chabauty method, and yeah, and there's a way you can make it work for integral points too, where you replace the Jacobian with the generalized Jacobian, and yeah, and then you're looking for integral points, and but it's the same idea, and that's what Skolem did in the context of powers of the multiplicative group. All right, so the last thing I want to do today well, except I won't finish it, is talk about Kim's rewriting of Chabauty in terms of the curve without mentioning Jacobian. So in terms of this étale homology group. So, and for this so the point is without mentioning the Jacobian. Yeah, so for this I'm following some nice notes that David Corin wrote up, who's hiding behind there. Yeah, so I've also put the reference to that in the abstract, which presumably will be posted somewhere soon. So, all right. So for this, so again, we're going to fix a prime p, and in order, I have to introduce some notation. Yeah, maybe I should say before I start. I mean, why do we care? I mean, why do we care that I use Jacobian? I mean, the advantage is if you rewrite Chabauty without mentioning the Jacobian, if you can express everything just in terms of the curve, then I mean, this is something that you can express in terms of the étale fundamental group of the curve, and this is essentially the abelianization. I mean, converted into a QP vector space. And so if you can do this, then Kim's idea was then, well, maybe you can use more of the fundamental group, not just the abelianization, but you can look at deeper quotients of the fundamental group, and you can get more information. And so that's what Kim is trying to do. But before you can even start doing that, you have to first get rid of the Jacobian. Okay, so yeah. All right, so the Jacobian is the enemy, as Peter Sarnak would like to say. He calls everything the enemy. Whenever there's a problem in a proof, it's like, yeah, you probably know that. Yeah. All right. Anyway, so the Jacobian is the enemy. All right. So for any abelian group M, I'll define the p-adic completion. So M hat. So P is fixed. So this just means the inverse limit of M mod P to the N as N increases. Yeah. So what is this? This is going to be a ZP module. Yeah, so this is a ZP module. So for various purposes, it's also nice sometimes to have QP vector spaces. So you can get one of those by taking this and localizing it by inverting P. And so I'll write it this way. So, or you can also write it as M hat tensor QP over ZP. And so that's what you do if you want to get if you want to turn M into a QP vector space. All right. Okay, so the setup is going to be this. And okay, now I'm going to, I mean, before I was talking about I was working over Q, but let me go back to talking about a general number field. Just because there are going to be a lot of other Qs and QPs coming up, and so it'll actually be easier to do it in the general case from now on. So, okay. So X now is a nice curve over K. And okay, so now I'll choose a prime of good reduction as before, except now it's a prime of K. So you can see it's become a curly P, prime of K. So this is at which X has good reduction. And then Roman P will just be the prime, will be the prime of Q that lies below this prime of the number field. Okay? So, right, so that's the setup. Okay, so now what we're going to do is we'll construct a diagram, a commutative diagram building on the sort of the Chabauty diagram. Okay, so there are going to be a lot of things in this diagram that are undefined, and so I'll have to postpone the definitions until next time. But okay, so we want to know the rational points of X. The old strategy of Chabauty was to consider it over the local field and consider the Jacobian over the local field, and also consider the Mordell-Weil group. And you know that the rational points of the curve must lie in both of these. And yeah, you can take the closure here of this one if you want to. And the way of studying this was to use this p-adic logarithm map, so which goes to the Lie group, Lie group of J over base change to this completion. Yeah, so Kp is the completion of K at P. All right, so the first thing I want to do is, well, I mean, this is a QP vector. This is a QP vector space. In fact, it's a KP vector space. So there's no harm. I mean, yeah. So Chabauty. Okay, maybe I should write this first. Chabauty says, understand the images of J of K and X of Kp in J of Kp. Well, in fact, not just in here, but actually go all the way to here in the Lie algebra, in this vector space. And so we want to replace everything. I mean, everything in this row involves the enemy, so we want to get rid of it. So yeah. So the first step is to say, okay, this is a QP vector space, so there's going to be no harm in replacing this with its QP vector space version. So we can p-adically complete it and take 1 over p. Actually, this just, because this is a finely generated abelian group, this is actually just the same as tensoring this with QP. You can do the same thing here. You can p-adically complete this, which actually doesn't do much because this is almost pro p already. So this just gets rid of the prime to p torsion. And then you can invert P and now make it a QP vector space. Yeah, and then you have, so you can do this. Yeah, so you're right. So, and then, well, this thing still maps to here because this is a QP vector space. And this turns out to be an isomorphism. You can just compare. I mean, you already know this is injective, and you can check dimensions, so that's an isomorphism. Okay, so now the idea is we'll use a Kummer map that sends this into here and sends this thing into the corresponding local H1. So these are Galois cohomologies, and where V is this thing here, which I'll have to talk about later. Yeah, and then you can look at this. This is kind of like the map from the Mordell-Weil group into the H1 of like the p torsion, except I've essentially taken the inverse limit over all p's, all powers of p, and also tensored with QP to make it into a vector space. And so you have this sort of Kummer map that just comes from the usual descent sequence that goes from here to here. And in between, but you want to understand this image because this is a very big thing, and so it's going to land. It's going to be bounded by some Selmer group. So except there's going to be some QP version of the Selmer group, just by taking an inverse limit of the p-n Selmer groups and then tensoring with QP. And then that's contained in here. Now, on the other hand, this will also be contained in something. In fact, it's isomorphic. The image of this thing in here is actually what Bloch and Kato denoted like this. It's some condition defined by some crystalline condition, which I'm not going to explain now. And you can also re-express this in crystalline terms. It turns out to be what's called the Bloch-Kato-Selmer group, which has a map here. Yeah, so this thing here is the Bloch.
Sorry, did you say what V was?
V is this, which I haven't really defined, but yeah. So, right, and then, okay, and then this maps. There's some localization map here, and there's an analog of this logarithm map here. There's something called the Bloch-Kato logarithm that takes values in some de Rham, well, something dual to de Rham cohomology, so which we'll call de Rham homology of x over this local field, and then modulo some part of its Hodge filtration of the yeah. And so okay, so and this turns out to be an isomorphism as well, and this, well, this is an isomorphism. This thing is probably an isomorphism. This is an isomorphism if Tate-Shafarevich group is finite, if a p prime part of that is finite. So yeah, so now the idea is, so this was the bad row of the previous Chabauty diagram, which is the top two rows, which was used to cut out the define analytic functions here that vanish in here. But now the idea is you can just replace that. It'll contain the same information if you replace it by this. And notice, the enemy is gone. There's no J anywhere in here. So this is all defined just in terms of this V and the Galois action on V. So okay, so maybe I'll say a little more next time about what some of these things actually are and how you define some of these maps. Okay, but that's it for today. Okay. So this V, that's V. I mean, yeah, I'll take homology. It's essentially in terms of the Jacobian, it's the usual Tate module tensored with QP. It's isomorphic to that. So it's, yeah. And as you know, Tate module is like a kind of homology, atal homology. Yeah.
So I have a question, not specifically about that, but in general about the Chabauty method. You have made the assumption that you're working over Q, now you remove that.
Yeah.
So when you do the Chabauty method, you work over a number field. So there's a part that you take the closure of the rational point, or the model value group.
Yeah.
That's a ZP module.
Right. It doesn't have a KP structure.
The curve has a K structure.
Right.
And you should gain something by being on this.
Right. You should. Yeah.
But you don't, right?
Well, sometimes you do.
Yeah,
sometimes you do. Yeah. So various people have worked on this. So I think Samir Siksek did something with this, and also my student Nicholas Triantafilou wrote a thesis where he examined this quite systematically and tried to study, well, actually he especially studied I mean, it's kind of hard to prove general theorems about that because you need to know some things about the ranks of the Mordell-Veit group. But what he did was he studied the analog for Skolm's method in the context of subvarieties of tori. And there where you know all the ranks by the Dirichlet-Essien theorem. And he can characterize exactly when this kind of method works, when you get more information. So essentially what you do is you take the restriction of scalars of everything, and then you work with the restriction of scalars. So now your curve is now higher dimensional, but everything's higher dimensional. So your Jacobian is now also higher dimensional. And your Mordell-Weil group is just what it is. It's just this ZP. And then everything's over QP again, and you can do the intersection there. So you can read Nicholas Triantafillou's thesis. Okay.
Yes. If you look at the spoiler appartement, I think we prove that this of KP intersection with H1F of KP is finite in H1DR with KP over 0. Are you going to prove the same things? I think we're going to prove that the intersection of x of KP on the H1F of KP, the global Lopez number group, is finite in H1DR of KP over 0.
Okay, so if I understood the question, I mean, what happened here was if you had the suitable rank condition, the rank was less than the genus, then it turned out that the images of these two, the intersections of these two, of the images here was finite.
Yes.
And that was important. That gave you a finite upper bound for the rational points. Not equal necessarily, but an upper bound for the rational point. So the question is, can you do the same thing if instead of mapping these two things into here, if now you're going to be taking this and this and mapping everything into here?
Yes.
Now, well, the point is that this is essentially the same as this diagram here. I mean, this is literally isomorphic to this.
Yes.
And this one here is well, it's I mean, at least if Shaw is finite, it's actually the same as this. And anyway, I mean, if you're going to use this method anyway, the only way you would compute the more group of rational points is by doing summer group calculations anyway. So you'd only, and in all the contexts where you'd want to apply this method, you will know that the dimension of this is actually less than the dimension of this, which is G. This is G dimensional still. It's still this. And so it's actually this really is just a rewriting. There's no new information in the diagram. It's just a way of rewriting the usual Chabauty method without referring to the Jacobian.
Yes, but only if you know that the Chabauty group is finite.
Okay, but then it's just a minor modification. You replace the closure of the Mordell-Weil group by the image of the Selmer group. So what you need is that the dimension of the Selmer group is less than the genus. But the only way you would know that the rank was less than the genus is by proving that the Selmer group was less than the genus. So, yeah, so you really haven't lost anything.